Physics notes, Unit 18A, electrostatics. Exactly what it says it is. Electricity at rest, static. And you know this from experience, like you get static in your hair, especially in the wintertime when things are drier. Static electricity in your like dryer. You put like fabric sheets in there to eliminate some of the static. Or in the wintertime, if you're walking along and sometimes you get a little shock because you get some charge on your body from carpeting and other surfaces. So electrostatics, study of electric charges at rest. And we let them jump around. Those little shocks those are movements of charge, but they're moving because they're built up. And we'll talk about actual currents in the next unit, but we're just talking about charges that are building up and could jump around. And we'll talk about how they jump around and how to transfer them from one place to another place. But there's two basic charges, and here's something interesting about this unit. And, well, it connects to chemistry a little bit. In chemistry, you all know that electrons orbit the nucleus. The nucleus is protons and neutrons. And what keeps the electrons in orbit is that electrical attraction. And basically all of chemistry is based on this principle. Like if you're missing electrons, then you're a positive ion. If you have extra electrons in your shells, in the outer shells, you're a negative ion. And this is really the guts of chemistry. But like in chemistry, when you say something is missing 2 electrons, that means it has a +2 ion. You say it's +2, but you never use the units because you don't have to, and it's better to do it that way in chemistry. You just talk about the absolute number of electrons that are either missing or added to a particular orbital shell. But it turns out, well, we know electrons are negative. We know they're negative. But what is the actual, when you get down to it, the measured actual size of the charge? Turns out that electrons are negative. This is probably the first time you've heard this, maybe, unless you've taken physics before. Negative 1.60 times 10 to the negative 19th coulombs. C-O-U-L-O-M-B-S. Like I say, in chemistry, you just said, oh, it's just -1. Okay, because you don't need all these units and all the particulars. You're just looking at comparisons. And a proton, even though it's like 2,000 times more massive, has the same positive charge. So we usually don't put the plus there, but it's the same magnitude. It's that many positive coulombs. Turns out that unit's very small. Obviously 10 to the negative 19th is very small as far as the size of a unit. And these are fundamental charges, and all other charges are basically multiples of those. If when you have something that has a bunch of electrons on it, I'll do a problem in a few minutes here, you have to have a multiple of these charges. So more on that coming up. But what are the units? Coulombs. Named after a famous scientist. Capital C for coulombs. It gets a little tricky because capital C can sound like it stands for charge. We're going to use the letter Q for charge here. You'll see that in a few minutes as well. So we got to get used to this. We got to practice it. But coulombs, the symbol for coulombs is C. The fundamental rule, once again, very simple to start off. Fundamental rule, we all know this, probably in 5th grade, 3rd grade. Like charges repel, and opposites attract. Right? 2 negatives repel, that's what we mean by like. Or 2 positives repel. 2 protons repel, 2 electrons repel. But electron and proton attract. Which brings us to these questions here. What keeps electrons in orbit? Well, electric attraction. They're attracted to the protons. Attracted to the protons. Because the protons are in the nucleus. And the electrons are orbiting because they're attracted. They stay in orbit. That is basically the centripetal force. It's the force of attraction that keeps them circling. It's a little bit more involved than that, but it's the basic idea. But here's an interesting question that, once again, maybe you haven't thought of. The nucleus. What keeps the nucleus together? The nucleus is a tightly packed, it's roughly, the smaller elements are half protons, half neutrons. And neutrons are neutral. There's no electrical attraction or repulsion. But when you get to the big atoms, there's extra neutrons in there. We don't need to worry about that. But there's all these protons together. And they're repelling each other. So they don't want to stay together. So what keeps that nucleus together? Well, some of you know this. There are two more forces. In nature, there are four forces. That's what we believe right now. It's the common theory in physics and science. There are four fundamental forces. There's gravity. It's a force of attraction between things that have mass. Then there's what we're going to be talking about now, the electrostatic force, or electromagnetic force, that can be attractive or repulsive depending on whether the two charges are like or opposites. And then there are what are called the strong and the weak nuclear forces. They're short-range forces that are acting or active in the nucleus. So what keeps the nucleus together? Some forces that are actually stronger than the electrostatic force of repulsion. We just call that the strong and weak nuclear forces. Strong and weak nuclear forces. And we're not going to calculate those. I'm just saying those because it's just to be an educated person here. So strong and weak nuclear forces keep it together because otherwise the electrostatic force wants to blow it apart. So let me show you a little video here on the fundamental rule. Let's try this. So here we have some physics professor holding up two balloons that are uncharged. I'm going to talk through this because the audio is not the best. And so they're not exerting any force on each other. What she's going to do is she's going to rub them in her hair. It turns out that your hair, especially on dry days, and in winter this works better, your hair picks up electrons. And when you rub the balloons, which are rubber and insulator, in your hair, they get a little localized charge. So she's rubbing both balloons in her hair, so they're both picking up the same charge. They could be both positive for all we know, but it turns out that they're both negative. So they're like charges. And then when she holds them up, you'll see that they now will not hang straight down. They're pushing on each other. Now, they're also attracted to the sweater, which we'll talk about later on. But the main thing here is, forget her sweater right now. They are repelling each other. Like charges repel. So that's a good example of at least the first part of the fundamental rule that like charges repel. And as I was ready to mention there, that later on I'll show you opposites attracting, but that's like charges repelling. Then we have this idea of conservation of electric charge. Charge cannot be created or destroyed, only moved around. And bottom line in most of these demonstrations, what's moving are electrons because they're loose. They get loose in the air because they're orbiting the nucleus. Protons are harder to come by. They're in the nucleus, and they're harder to get out of the nucleus than the electrons are. The electrons get bumped around, and once again, chemistry is mostly about the electrons getting bumped around or moving from one atom to another atom, filling up those orbital shells. And most of this is what it is as well. In electricity, like in wires, it's mostly electrons moving, not protons. We'll talk more about that as time goes on. For example here, it turns out like when you rub rubber, or most plastics, styrofoam, you rub them with fur or hair, almost always you are rubbing electrons off of that object, off the fur, onto that object. So when you rub a balloon in your hair, it picks up electrons. And here, the balloon, it says, say that balloon that woman rubbed in her hair, the professor, picked up enough electrons to build up a negative 0.15 micro is 10 to the negative sixth on the fur. Now the question here is on the balloon. It says, what is the resulting charge on the fur? Well, on the fur, the charge on the fur, or loss of charge on fur, if the fur happened to be neutral to start with, it says if the fur was neutral, then the fur is going to be plus 0.15 microcoulombs. It picks up the equal and opposite charge because you're just moving electrons around. Now it also says, what is the resulting charge on the fur? That was it. And how many electrons were transformed? Well, here's the basic idea whenever you're asking about a numerical thing like this, when you have like a big number. It turns out that 0.15 microcoulombs is actually a big number compared to the charge of the electron. How many electrons does it take to make that? Here's basically a formula for you. How many big things, how many small things, in this case, the electrons, how many small things does it take to make a big thing? To make I'm just saying kind of a generic statement here, to make a big thing. Well, the way you do that is you just take the big divided by the small. So the general formula, so this is the question. This can be applied to a lot of things we do in this class. We'll do it in a little bit in some more sophisticated ways here in a homework problem. But you just basically take the big, and you divide by the small. Right? How many small things does it take to make the big thing? You know, how many quarters does it take to make $1? Well, you take $1 divided by 0.25 cents, takes 4 quarters. I mean, we know that off the top of our head anyway. But take the big divided by the small. So the big here is 0.15 coulomb, micro, okay? And I'll write it down as microcoulombs, divided by 1.60 times 10 to the negative 19th coulombs. So I'm taking the big divided by the small. That's the big, that's the small. Now, you have to remember here that this is 0.15 times 10 to the negative 6th. So I'm going to plug that in my calculator. 1.60 times 10 to the negative 19th is already in its scientific form. It's a matter of, so that those are both now in coulombs. So it turns out the units cancel out, and you end up with 9.4 times 10 to the 11th. The answer is 9.4 times 10 to the 11th. That's a number that hasn't, there's no units there. That many electrons, you can say it's that many electrons. It just says how many. You can say how many cars go down your street in an hour. 16 cars. So it's a number. It's not really a unit. Anyways, that's how you figure out how many small things it takes to make a big thing. That's how many electrons were rubbed off the fur and went onto the balloon. So that's how many excess protons now the fur has. It has that many excess protons. Not because the protons are moved around. It just is missing that many electrons. All right, then we have something that you might have done if you've done it in high school. And if you didn't do it in high school, that's fine. We have this thing called a Van de Graaff generator. And it's a device used to create large static charges on a metal ball. And it looks a lot like this. You've probably seen some demonstrations like this before. You can go online and type it on YouTube, Van de Graaff generator demonstrations. And the famous one is like if a person stands there and touches it, their hair stands up on end because it transfers charge to the person. Very famous experiment. And when you're dealing with these things, they're kind of fun in class. I have one in my own class. They give you little shocks. Some people like that. Some people hate it. I mean, it doesn't always feel good. And they generate actually high voltages. So and we'll talk more about voltage in the next unit, but they're fun. And I'll show you a demonstration here in a few minutes with this Van de Graaff generator. But bottom line, what happens is this over here. This is a picture from the book. There's a metal sphere, and inside there's kind of like a comb inside here. It looks like a comb. It doesn't have to look exactly like a comb, but it's metal. And there's a roller up here with a rubber. This is a rubber band. This is a rubber band belt that goes around and around. When it's turned on, you can either crank it or there's an electric motor that turns this around. Then there's a comb down here at the bottom. It's attached. This symbol right here means to the ground, to the earth, to like the table which is standing on a desk, which is touching the earth. So that's the generic symbol for ground. Oh, it says it right there, ground. So more on that later. Ground. That's the symbol for ground, electrical symbol for ground. That means you're touching the earth somehow. Okay, literally the ground. But this rubber belt goes round and round. And what happens is this belt, okay, what it's doing is actually taking off electrons. When you take electrons off of something, it becomes positive. That's what's happening here. And a little bit of a misconception here. I don't personally like exactly how they drew this, because when you have a metal ball, and the metal ball has a little bit of a thickness, they're showing like positive charge on here, that's the excess protons. There's millions and billions of other protons in there. That whenever they show things that are charged, they're showing the excess of charge. And the excess of charge here is because they took off 50 million electrons. That's why it's positive charge. But furthermore, what they should have done is they should have put the charge on the very outside. I like it when they put the charge. So in other words, it turns out that anytime you have a conductor, metal is a conductor. Basically, that's really all that is, a conductor is metal. So pretty much everything else, and there's variations on this. But I'm putting the pluses on the outside. They're not really on the inside. They're not actually in the metal. They're on the actual surface of the metal. And since it's a round ball, they tend to stay on there pretty well unless you get close. They will discharge through the earth or through the air. If you get close with your finger, it'll send a little shock or a little spark, like a little lightning bolt to your finger. All right, but when you're touching it, it's spreading out charge on your body right there, and some of that charge, if you're standing on the ground, is going to the ground, so you're not getting shocks. The shocks are what hurt you or feel a little bit of a pain. But once again, I like to put the charge on the outer surface. The charge does not stay in the middle. And once again, a positive charge means you took electrons off of there. So let me show you a little video of a Van de Graaff generator. All right, Van de Graaff generator, which is over here. Here's the top ball that's going to be charged. I haven't started the video yet. The audio, once again, I'm going to talk you through the audio. He has this discharge ball here. If you touch it with your finger, you get a little poke. You're going to see some sparks that jump because it will discharge. When the charge gets strong enough, it'll discharge through air, even though air is an insulator. You'll see it, and in real life, when you have one of these in a room, it makes a big cracking noise. And when it hits your finger, it's a little bit painful. It doesn't really hurt you unless you have a really, really big Van de Graaff generator. Even then, it's usually not fatal. Well, it's not fatal, but because of certain conditions. But let us just look at the demonstrations. It's safer to have this ball. So you can see there's a spark. Okay, he's going to use this dummy head, and you're going to see the hair start to stand up because now we're charging the hair, and the hair is going to, because it's touching the ball, and then charge is being transferred to the hair. He's going to zoom in here, so you can start to see the hair go kind of frizzing out here. And then he'll bring the discharge ball close to it, and the ball is oppositely charged to the hair, so it attracts the hair. Opposites attract. Then every time he discharges, you see a big spark. Every time he discharges, the hair goes down a little bit because it's taking some of that charge away, so the less charge in the hair, the less it repels each other. That's a fun demonstration. Now he's going to put some aluminum pie pans on the ball here, and they're going to pick up charge and repel one another, like charges repel. So that's a fun one. The electric pie pans, the aluminum pie pans repel each other. Now, this fluorescent bulb. So electrons are transferring from his discharge up here through that bulb. It doesn't take a whole lot to light up the bulb. So I'm just going to stop it now. All right, so yeah, so the Van de Graaff generator is a good way to have some fun transferring some charge around and showing the fundamental rule. Opposites attract, likes repel. Showing how you ground as a ground within the Van de Graaff. And that ball that he had in his hand was also acting like a ground, bringing the charge away and back to the earth. All right, so now let's get down to some real nitty-gritty here. There are four fundamental forces in nature, which I alluded to earlier. There's gravity, the electromagnetic force, which is what we're basically dealing with here, electrostatics. The weak and strong nuclear forces, which we're just going to mention that. But here we have, well, here's a review. Newton's law of universal gravity. We did that in Physics 201. We did it in a previous physics class. The force of gravity is attractive only. It's proportional to the product of two masses divided by the distance squared. It's an inverse square law. If you double the distance, you have 1/4 the force. All right, so now, let me get back here. We have Coulomb's law. And it doesn't take a whole lot of observational skills here to figure out that Coulomb's law, which has to deal with electric charges, is of the same format. It's very curiously the same. So actually, there's a lot of scientists, physicists, trying to incorporate these two laws into one law because they look like they have a connection because they're the same format. So instead of the gravitational constant G, now we have Coulomb's constant K sub E, which will be given to you over here on the right hand side, 9 times 10 to the 9th Newton meter squared per Coulomb squared. The problem's going to be very similar to the problems we did with universal gravity, except for now we have repulsion as well as attraction. So the vector nature of these things gets a little bit more involved, as we'll see in a minute. But it's the product of the two charges, so it's always a force between two charges. Charge number 1 exerts a force on charge number 2. Charge number 2 exerts a force on charge number 1. It's the same force, even though the two charges might be different sizes, and they are different charges. They exert equal and opposite forces on each other. Newton's third law, divided by the distance squared. Once again, the distance is from center to center. A little easier here because usually we have small charges, so it's assumed you're at the center of the charge, which is pretty easy to assume when you have a little pinpoint of charge. So let's start off with a little practice problem here. Coulomb's law. Once again, the charges are measured in coulombs. The distance has got to be measured in meters. calculate the force of attraction between 2-point charges of that many coulombs if they are separated by 47 centimeters. So I'm going to plug into this equation up here in this box, which you can barely see. You can probably see it in your notes. I'm just going to plug into that. The force, actually, I'm going to draw a little diagram here. So we have a 2 coulomb charge. That's the 2 coulomb charge, 2.0 coulombs. And we have the 3 coulomb charge. They're both assumed to be positive, unless you're told otherwise. They're like charges, in other words. They're not the same size, but they're like charges. So if you were to draw a free body diagram, they are repelling each other. I'm going to call that F1. They're like charges, they repel. And I'm going to call that F2. But F1 and F2 are the same force. They're repelling each other, equal and opposite forces, because of Newton's third law. It's the electrical force. Now I've just plugged in the actual force for both of those. I can just call it F, is K. That goes in the numerator. 9.00 times 10 to the 9th goes in the numerator. It's out front there because it's a coefficient that's constant up here, but it goes in the numerator, like big G in the gravitational equation, times 2 coulombs, 2.0, 3.0, divided by the distance in meters. It's 0.47, so be careful with that, 0.47 meters squared. Don't forget to square that. So if you plug that all in, you might want to pause this and do that, but I did it earlier. It comes out to be 2.4 times 10 to the 11th. 2.4 times 10 to the 11th newtons, repelling. The direction isn't as important right now, but it will be eventually. So I'll get used to sticking with labeling the direction, repelling. And what you're going to notice about that, it's a very large force. That's very large. It's a very large force here, because it turns out that coulombs are a large unit. Well, are large if you have 2 coulombs, because most things in life, as you'll see in the next few questions, or electrons in particular, 1.6 times 10 to the negative 19th coulomb. So if you have 1 coulomb of charge, that's a lot of charge. That's a lot of electrons. A lot of electrons, or a lot of missing electrons. So a coulomb by itself is a very large charge. Okay, you didn't need to say that. I'm just kind of pointing that out. All right, another similar problem or application of this same law. Now you got to figure out how far apart 2 charges are. So now we're dealing with micro, because that's more common. Micro is 10 to the negative 6. We did one problem like that already. But both of these are micro, micro, and micro. And the second one's a negative 3. And in this case, all right, you have a plus 5.2. Once again, it's always positive. And then you have a negative 3.3 microcoulombs. That's a micro. And they attract each other. You don't have to, for these basic ones, you don't need to draw them, but eventually we'll need to draw these. Once we get to more complicated diagrams, you'll see that in a minute. But that's the same force for both of them. You call it F1 and F2, which will be, like I say, more important as we go along. But F1 and that's F1 and F2. They're the same force, same size force of attraction towards each other. F2. You could just call it F in this case. So in this case, once again, I'm going to plug into that equation at the top there. Well, I can write it down. F equals K Q sub 1 Q sub 2. My Q's don't always look so good. Over R squared, the distance squared. But I know the force in this case. The force in this case is what? 0.75. So I got 0.75 equals 9 times 10 to the 9th. Always goes in the numerator. Times, I'm going to erase this so I have space. Hopefully you got more space. All right, times 5.2 microcoulombs. 5.2 times 10 to the negative 6, just to remind you. But usually I just put the symbol for micro in there, and I have to remember to put that in my calculator to make it go faster. But here's the other thing. The negative 6 is important. It's negative 6 microcoulombs. But the negative 3 is not important. You don't need to put the negatives in the equation. All that negative tells you is that these attract each other. So you don't need to put the negative in the equation for these. You can if you want. I prefer not to. It's only all that helps you to tell you is whether they're attracting or repelling. But the negative 6 is very important. Very important. Divided by, what we don't know is the distance. R squared. Some books will have a D there instead of an R. So 0.75. So if you multiply all those numbers in the numerator, multiply all those numbers in the numerator, you get 0.15. I hope I did that right. 0.15 over R squared. And then if you switch things around, I'm going to go over to the right here and just keep doing the algebra. That means that r squared equals 0.15 divided by 0.75. That's algebraically equivalent. You can divide that, you get r squared equals 0.20, and then you take the square root of both sides, you get r equals 0.45 meters is how far apart they are. That's 45 centimeters. So there we go. That's how far apart those two are. And once again, you don't need to put negatives in the equation. You never have to put the negatives in the equation. All right, compare the electrical force between a proton, electron, and a hydrogen atom. Okay, hydrogen, the most abundant element in the universe. The sun, the stars, and in the sun and the stars, it's fusing to give off energy. Don't need to know that right now. But basically, hydrogen is just one proton, one electron. You get the proton in the middle. That's the proton. And then we have the electron. It's small. It orbits. That's supposed to be the electron orbiting. It's orbiting because they pull on each other. All right? And that's the force of electricity. They pull equally on each other. It's for the electron, it's the centripetal force. The proton basically doesn't budge at all. It's wobbling a little bit. But for the electron, it's certainly the centripetal force. We don't need to use the centripetal force equation right now. It just says compare the gravitational force to the electrical force. I'm going to do this one a little bit faster. So the electrical force is going to be 9 times 10 to the 9th times charge number 1, which is an electron. Now, once again, the electron down here to the left is negative 1.6, and the proton's positive 1.6, but you don't need a negative there. It's going to be 1.6 times 10 to the negative 19th, 1.60. All right, and I can just square that, or I can write it out again. It'd be faster just to say it's squared, 1.60 times 10 to the negative 19th, because the electron and proton both have that same charge, divided by that distance of orbit, which is 5.29 times 10 to the negative 11th squared. I'm going to do that math for the electrical force, and I'm going to do the math for the gravitational force, so you might want to pause this after I write this all down. All right, so you probably want to pause this and write this down, but I did all the math there. You might want to double check that with your calculator. Make sure you can plug all those numbers in. It's a lot of numbers to plug in. Multiply all the top numbers, use the parentheses if you have to, and make sure you square that denominator before you divide it into the numerator, and you get the electrical force, which is small, but when you do the gravitational force, which is a review question, you also have to plug in capital G, looking back or looking it up, 6.67, that's the universal gravitation constant, times 10 to the negative 11th, times the two masses that were both in kilograms, divided by the same distance, once again squared, you get this force of gravity, which is very, 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 very small. The point being here is gravity is insignificant compared to the electrical force, which was small as well, but they want you to compare the two. Well, the way you compare things, once again, is you take the big one over the small one. Take the force, the electrical force, over the gravitational force, if you want to compare them. So it's going to be 8, that's 8.2 times 10 to the negative 6th, divided by the 3.6 times 10 to the negative 47, which equals roughly 2 times 10 to the negative 39th. 2 times 10 to the negative 39th. That's the ratio of Fe to Fg, which means that Fe, the electrical force, is roughly, all right, well, basically, forget the 2. It's 10 to the negative 39th times the force of gravity. I'm sorry, that should be positive 39. I made a mistake there. That's a big mistake. That's positive 39. It's a bigger force, not a smaller force. The other way to think about that is that when you divide by a negative exponent, you're basically adding the 47 to 6. So it's 10 to the 30, positive 39. Okay, so the electrical force is a 10 or 1 followed by 39 zeros times bigger than the gravitational force. I don't even know if there's a word for that. Billion, 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 billions. So bottom line is the electrical force is what keeps the electrons in orbit, not gravity.